Welcome to the Beer's Law Learning Objective lesson. So it's a short mini lesson on just Beer's Law. So within this is the end of our notes. We should be able to explain how the absorbance of a colored solution is related to its concentration, and then also to be able to determine the concentration of a solution given and the absorbances of the solutions with known concentration using Beer's law. Now Beer was a scientist. It was Beer-Lambert, so it's actually the Beer-Lambert's law, but we often just abbreviate it to say Beer's law. So he never really gets all the credit because we're lazy. All right, so just to start off with, Beer's law talks about the color of different solutions. So when you dissolve a solution, right, you have some dissolved solutions right here. There can be different colors, right? They can be all the colors of the rainbow, right? Roy G. Biv. Depending on the concentration of that salt, that colored salt in the water, if it is super concentrated, it's going to be a darker color, right? So over here at test tube number 7, that's very concentrated because it's a dark green. Whereas over here at test tube 0, that's going to be less concentrated, right? Because it's a lighter yellow color. So there's less. In this case, this picture here is ammonia, NH3. So there's yellow if it's not that concentrated, so it's more dilute, all the way up to more concentrated if it's darker. And we can actually use that color spectrum, that wavelength of color, to figure out exactly the concentration of whatever that salt might be inside of it. And so colorimetry or spectrophotometry, it is just the measuring of color, the measuring the appearance of light. So if you remember back to our previous unit on atomic structure, electrons get excited, and when they get excited, they absorb some energy, and the moment they drop back down, they're going to release that energy, right? And so I'm going to go ahead and draw that just to remind you. I'll draw it off to the side over here. So say this is n equals 1, n equals 2, right? So this is our Bohr model. Our orbitals are fixed quantities. So there's an electron on this first orbital right here. If there's energy that gets put into this electron, it's going to get excited, right? So say it goes to the n equals 3 level. This electron now has to go back down. So after it gets excited by a certain amount of energy, it's going to drop back down, right? And if it drops back down to, let's say, n equals 2, so the second energy level, it's going to release a wavelength of light. Right, that's my beautiful wavelength of light right there. And remember, at 3 to 2 was red light, 4 to 2 was like a bluish, greenish light, and so on and so forth, all the way from 6 to 2, which was like a violet purple light. So when you release those energies, those wavelengths of light, we get Roy G. Biv, right? We get the electromagnetic radiation spectrum. So we have all the way from like UV light, infrared light, microwaves, radio waves, X-rays, so on and so forth. But the part we care about for this, for the colorimetry, is just the spectrum that we can see. So red to violet, right? Roy G. Biv. Remember, red was around 620 to 700 nanometers of wavelength, whereas violet was on the 400 spectrum on that side, right? And remember also white light, it has all the colors. So when you look through a prism at white light, so the sun, for example, it's going to come out with all the different colors, Roy G. Biv, right? All the colors of the rainbow. That's why rainbows exist. Well, every substance, at least to the human eye, is reflecting light. And the color we see is that reflected light. And so if we have all these colors, all Roy G. Biv being absorbed, so this apple is absorbing all of the Roy G. Biv colors, right? So it's absorbing Roy G. Biv. So red, orange, yellow, green, blue, indigo, and violet. Well, the color we see when we look at an apple is red. So that means it's absorbing orange to violet. It's absorbing all of those, but it's not absorbing red. Instead, it is reflecting red, and that's why we see it as red. So whenever you look at something, it's absorbing the colors that you do not see. It's reflecting the color that you do see. So if we look at red Kool-Aid, right, it's reflecting red, but it's actually absorbing green. If we look at something that looks purple, it's reflecting violet or purple, but it's absorbing that yellow color, right? So the opposite color on the spectrum, right? So some color theory if you're an artist, whatever color you see, it's absorbing the rest of the colors and it's absorbing the opposite color the most. All right. So we use that, the colorimetry, that reflection absorption, to create a serial dilution. And serial dilution just means we have some unknown solution, right? So number 7, we don't know how much ammonia is in this here, this particular sample, right? So ammonia is a byproduct of most mammals. It's in our pee, right? So ammonia NH3. And if it's in too high of a concentration in water sources, it often kills the aquatic life. And so a lot of environmental chemists, they measure the concentration of ammonia, right? And so we want to find the concentration of ammonia. And remember, concentration can be signified with brackets around whatever compound you're talking about, or you can say big M for molarity, or you can say moles over liters, right? So we're trying to find the concentration of ammonia, and it's number 7. This is our unknown. But that's too dark, right? And so we're going to dilute it a couple times down to 6, to 5, to 4, to 3, to 2, to 1, to 0. And the way we do that is we take a little bit from the unknown, we place it into a new test tube, we add some water. Then we take that, we put it into a new test tube, add some more water. Take that, put it into 2 test tube, add some more. And you can keep doing that, right? So it's usually on a 1 to 9 part ratio. So we take 1 part from the previous one, we add 9 parts of water to the next one, and so we end up with a total of 10, right? So the first time we dilute it by 10, the second time we dilute it by 100, the third time we dilute it by 1,000, and we keep going by a factor of 10. So we're on a logarithmic scale. And so once we have all of our solutions diluted down, and we know exactly how much we diluted it down, and we can calculate how much we dilute that down by using our dilution formula. So M1V1 equals M2V2, or in our notes, I believe it's the molarity of the concentrated times the volume of the concentrated equals the molarity of the diluted times the volume of the diluted, right? So you can figure out, you can calculate how much it is each time by what your first molarity was, or what your first concentration was, times your volume, and then so on and so forth. Once we have all of those samples, we use this guy right here called a spectrophotometer, or a colorimeter, right? And we actually have one of these in the classroom. And first step is to always calibrate it with water, right? Water's colorless, or it should be colorless, and so all the light is going to transmit through it, so that's 100% transmittance. Once we have that calibrated, we're going to go ahead and place our samples in this little box right here. And it's going to basically do what this says over here, this diagram, right? So there's a light source here, somewhere in this box, and that light source is going to go ahead and pass through a color, right? And this knob right here, you're going to set it to what color you want to pass through. So if we have a green solution, right? If we have a green solution, remember that it's reflecting green, it's absorbing red. So we want to put the wavelength to a red color. So using this right here, this little knob, we're going to go ahead and place that to like a red color if we see green, right? So we're going to have red go through it. And depending on how much light can get through this cuvee, and a cuvee is just a really tiny test tube. It's usually square or like cubical. Depending on how much light can pass through it, it's going to give us an absorbance value or a transmittance value, depending on what we set the actual machine to. And we can use that data to then make a graph and figure out exactly what the concentration might be. And so here, right, we have a less concentration, so more light will get through. And then number 7, test tube 7, it's more concentrated, so less light will be able to get through. So colorimetry, or colorimetric, or spectrophotometry analysis, that's just the measuring of colors, right? So it's the measuring of colors or the appearance of light. right? So it only works with colored solutions. If we have a colorless solution like water or maybe salt water, right? Salt, we can measure the concentration of salt, but it's colorless, so we wouldn't be able to use this technique. It has to be an element or a compound that when dissolved in water, it creates a color. So we can use food coloring, we can use copper sulfate, so on and so forth. But if it's colorless, we can't use this technique. And the spectrophotometry, that is that machine, and we're going to use that to figure out the degree of light that is absorbed by the colored solution to determine the concentration of that solution. So we use the spectrophotometry to find the degree of light that is absorbed by the colored solution. Right, and it has to be a colored solution or else it won't work. To find or to determine the concentration of that solution. I'm going to abbreviate concentration as CONC. Of that solution. Right, so the darker it is, the more concentrated it is, the lighter it is, the less concentrated or the more dilute it might be. Right, and so that, again, this is a more simplified picture right here of the spectrophotometer, what's happening on the inside. So we have that white light that we're going to go ahead and set that wavelength depending on what is reflected, what is absorbed. And that light is going to pass through that solution, right? And so this is our solution right here. And this guy down here is called the cuvee. And the cuvee is usually kind of like a cubicle. If you Google a picture of it, it kind of looks like that. That's a terrible drawing. But the length of the cuvee typically is 1 centimeter. So whenever we plug in the length of our cuvee, we're typically going to plug in 1 centimeter for that. The light that can pass through, so this is going to be 100% light over here, right? We're going to put all the light we can. This over here is how much light actually comes out of it, right? And so this is called transmittance, and transmittance is just the degree to which light passes through a solution. I apologize for my handwriting. Don't have much practice using my Wacom tablet. This is a exercise for me. The transmittance, therefore, can be determined with a simple ratio, right? So our transmittance, big T, is just how much light actually passed through divided by how much light we started to put through it, right? And if you multiply that by 100, you can get a percentage. So it's how much light actually passed through divided by how much light we put into it. And that will tell us our transmittance. All right, absorbance is how much was absorbed, right? So if there's say we have 50% of the light got through, right? That means 50% of the light was absorbed. So the absorbance is inversely related to transmission, or transmittance, I should say, and it's directly related to concentration. So it's how much light is absorbed, and it's inversely related, I'll do this in green, it is inversely related to transmission, and I'll put transmittance, I'll put big T for transmittance, and it's directly related to our concentration. Right, and I'll put CONC dot for concentration. So that means that if we have an inverse relationship to transmittance, we can say that A for absorbance is equal to the negative log of our transmittance. And so that's how Beer's law kind of takes place, takes shape, right? So the inverse in this case, because we're by 10, if I go back to this previous slide, right, we're going by 10 every time, right? So there's 1 part to 9 parts, which equals 10, and we do that again and again and again. So it goes 10 to 100 to 1,000 to 10,000, so on and so forth. So we're increasing on a logarithmic scale. And so that's why we use log as our inverse, negative log as our inverse here. And so if we look at Beer's law, what it actually states, the actual equation, is the following. It's A for absorbance equals epsilon, so it's like a backwards 3, it's the Greek letter epsilon, which is our extinction coefficient, L for our length of our cuvee, which is 1 centimeter, and then C for our concentration. So A is unitless, it's absorbance, there's no unit for it. E is our extinction coefficient. And our extinction coefficient usually has a unit of molarity, 1 over molarity and centimeters, right? And then our L is our length. And our length of our cuvee is almost always going to be 1 centimeter unless it's said otherwise. That's just how big that cuvee is, how much room or space is it actually, the light actually passing through. And then C is our concentration, right? And C, concentration, is just molarity. So our unit for that would be molarity. So let's go ahead and look at some examples, put that to use. So absorbance versus concentration. If we do a Beer's law lab, if we use a spectrophotometer and we get some data, we can put that data on a graph. And the graph here shows absorbance on the left on the y-axis and concentration, which is molarity, moles over liters, on the x-axis. And we can figure out what something might be based on this linear graph. So we have 2 data points. So at 0.2 molarity, the absorbance was a little below 0.3 absorbance. And at 0.5 molarity, the absorbance was at 0.7. And so as there's more concentration, more solute in our solution, it's going to be much harder to transmit light through the solution, so it's going to be more absorbance. Whereas if there's less concentration, less solute, there's less absorbance, so there's more transmittance. All right, so we can use that data, we can use that graph to go ahead and answer these next 2 math questions. So the example says a 0.2 molarity solution of cobalt chloride has an absorbance of 0.27. Assume the length of the cuvee is 1 centimeter. First bullet point says, what is the value of the molar absorptivity or the extinction coefficient of cobalt chloride? So we're going to go ahead, underline what they gave us, circle what they're asking us to solve for, right? So they gave us 0.2 molarity solution, so we know that's our concentration. We know that the absorbance is 0.27 and that the length of the cuvee is 1 centimeter. It's asking us to figure out what the molar absorptivity or the extinction coefficient is, and I apologize for my terrible handwriting. All right, so we're going to go ahead and list what we have. So we have A for absorbance, our extinction coefficient is that fancy backwards 3, L for length, and C for concentration. So our absorbance is 0.27. Our extinction coefficient, or our molar absorptivity, that's what we're trying to solve for. And remember, the unit, when we get it, should be 1 over molarity times centimeter. Our length was 1 centimeter, and our concentration is 0.2 molarity. We're going to go ahead and plug all of that in, and then PEMDAS it out, right? Figure out what it might be. And so we have 0.27 for our A. We're trying to figure out our extinction coefficient. Our length is 1 centimeter, and our concentration, or molarity, is 0.2 molarity. All right, so multiply 1 times 0.2, divide it to the other side. We isolate epsilon, which is our extinction coefficient, and we should get a number or a value of 1.35, And our unit, since we divided centimeters and molarity to the other side, is 1 over centimeters times molarity. All right. The next bullet point here says, what is the concentration of the unknown copper chloride solution if the absorbance now is 0.38? So in this case, they want us to figure out an unknown concentration based on the same exact graph, right? So if we look at our graph here, that extinction coefficient, that's essentially our slope. It's telling us that's the relationship between concentration and absorbance every single time for cobalt chloride. And so our slope can be replugged in for this next example. And so we have a new absorbance, and we're trying to find a new concentration, but our molar absorptivity or our extinction coefficient is the exact same. And so we're going to go ahead and, I'll do it in red, list what we know, list what we have, and then figure out what we need to solve for. So same exact thing. We have absorbance this time of 0.38, and remember there's no unit for absorbance. Our extinction coefficient, we just solved for it, 1.35, and it's 1 over centimeters times molarity. Our length hasn't changed. Our cuvee, again, most cuvées are 1 centimeter. And now we're trying to find our concentration of this new solution. So we're going to plug everything in. We have absorbance over here on the left of our equation, 0.38. We have our extinction coefficient, 1.35. We have the length of our cuvee, which is 1 centimeter. And then we're trying to find our concentration. And our concentration, remember, is molarities or moles over liters. So we're multiplying 1 times 1.35, divide it to the other side. Our centimeters are going to cancel out. We're going to be left with molarity on the top side. And so our concentration or molarity, moles over liters, is 0.38 divided by 1.35. And so we get a value of 0.28 molarity. I hope this video helped. If you have questions, write them down and ask them when you have a chance.